please, there's a few announcements that are important to do with the assignment that are on Piazza that only about 50 people have looked at. The assignment's sort of designed not to be difficult, but it's also not designed so you can't just do it at the last moment. It's one of these things where you get stuck on something and then you go away and you think about it and you say, aha, now I know what it's about. So it's it's not something that you want to cram and do at the last night. Hopefully the 50 people is because you're all in groups of 3 and you've all shared a computer. But please don't leave it to the last minute. It's not difficult, but it's not designed to be done at the last minute. It's designed for you to do it, puzzle over something, and then say, aha, it's much simpler than I thought it was. Okay. And it's also not designed to just regurgitate things you've been taught. It's designed for you to discover things. All right, any questions about anything? All right. So what we've been doing recently is we've been looking at probability in terms of measures over possible worlds. The probability of a proposition is the measure of the set of worlds in which the proposition is true. Then the conditioning, all we're doing is just ruling out some worlds as impossible and then renormalizing. So that's all conditioning is. And then we have a belief network, so representation of conditional independence. In a total ordering of the variable, each variable is independent of its predecessors given its parents. Okay, so it's just a definition of what independence meant given its parents. Are there any questions about that? All right. So probably the best way to do this is just to go through a whole lot of examples, and we'll also make them all clicker questions because then I know whether what you're doing. So I'm just looking at this simple little network here with fire, smoke, and alarm. And in this, smoke is the only parent of alarm. And I'll even tell you the rule. Wait a minute. So smoke is the only parent of alarm, and fire is a parent of smoke. And I'll put up this. And the rule is that each variable is independent of its predecessors given its parents. That's the rule. Okay? So I want this, and the ordering here is fire, smoke, then alarm. And I want to know what this graph tells me. Does everyone know? So the only parent of alarm is smoke. And then the only parent of smoke is fire. And I'm asking about translating this bottom sentence into this graph and tell me what it means. Okay, so it's, do you know what a parent is? Okay, do we need more time? You want a bit more time? No. Okay. Right. It means alarm is independent of fire given smoke. Right? So that arc from there means that when we're given smoke, fire is independent of it. The only way that fire can affect alarm is to affect smoke. Right? So this is a smoke. Okay, does that make sense? You know what parent is? All right, let's go through this one more. So let's keep going. For the belief net, the only thing that's different is the diagram on the left has changed. The same order, fire, smoke, alarm. How are we going? Does anyone need more time? Oh. Some people said D. This says that alarm, given the alarm, this says the probability of alarm. This says the probability of alarm given fire and smoke, which is the probability of alarm given all its predecessors, is equal to just the probability of alarm. Alarm here only depends on fire. Right, that's what this graph over there says. The alarm given smoke and fire is equal to just depends. Alarm only depends on fire. So alarm is independent of smoke given fire. Is the right answer to that. Does that make sense? So the only parent of alarm there is fire. Are there any questions about that? In the bottom, so I should say what C means that the alarm is independent given nothing. They're independent of each other given no random variables, because we said before a tuple of random variables, just another random variables, and the other one's about independency. So this one here says that, okay, any questions about this? That's what this diagram tells us. Any questions? All right. Let's make sure. Here's another diagram. Alarm here doesn't have any parents. That's what this thing's, right? Doesn't have any parents in this graph. Oh. All right, how are we going? Need one more time, and it says, whoops. And the answer is C. They're just independent of each other. So it says that here that alarm and fire are independent of each other. There's no arc between them. They're just independent of each other. Okay, does that make sense? And we'll do one more. And now we have the same A, B, C, D, but now we have alarm has two parents, fire and smoke. How are we going? Do you need more time? Still need more time? Okay, 3, 2, 1, we'll stop. And the answer here is D. There are no independencies in here. This says the probability of alarm given smoke and fire is equal to the probability of alarm given smoke and fire. But this says there's an arbitrary probabilistic dependence amongst these things. Okay, any questions about what this means? It's just a statement about independence. All right. Let's do a few more different ones. Someone asked the question last time, I thought it made a good. Which network best fits the fire alarm that detects the heat of the fire? Right? The fire alarm up there, that smoke thing up there, that thing up there, the sprinkler, how it works is it detects the heat of it. It doesn't depend on smoke or anything. It just, if it gets really hot, if you fill up this room with smoke, it won't go off, but if you put a flame underneath it, it will go off. Okay? And I want to know which of these networks best fits such a fire alarm. Oops. I started up. Okay, how are we going? Anyone need more time? Let's stop. Right. So it says B, that it doesn't depend on smoke, it just depends on whether there's fire. Right, so the answer here is B. A says it just depends on smoke, but not on fire. So here, if I fill up the room with smoke, it won't go off because it just depends on the fire, not on the smoke directly. Okay, so it's independent of smoke. It doesn't matter whether it's smoke, whether there's smoke or not, as long as it's hot. Now I'll tell you, well, there's another alarm. Is there one in here? There probably is. There's probably a smoke alarm in here too. I can't see one. So if you're a smoke alarm, if you fill up the room with smoke, it'll go off. But if you stick a flame under it, it probably won't. So in your house, you have lots of smoke alarms, I'm sure. You should have them. If not, you should complain to your landlord. Yeah. So how are we going? Does anyone need more time? So how does a smoke alarm work? You think about, okay, let's stop. 3, 2, 1. Right, so a smoke alarm only depends on a fire because a fire produces smoke. That's the only way it detects fire. If you had a fire that doesn't have smoke, it doesn't go off. So it's independent. So this is a representation that the alarm here only depends on the smoke, not on the fire. And if we had some other sort of alarm that detects both heat and smoke, right, that detects both heat and smoke. Which one represents this? Okay, how are we going? Let's, getting there. Okay, do 3, 2, 1. Oh, it's more coming. 3, 2, 1, stop. Right, the answer is D. Right, it's not independent of each, and each of them provides some information about what you're doing, about what's going on. And just because I like giving... And which fits a burglar alarm? How do burglar alarms work? Burglary alarm works, right? Right, so which one here best fits a burglary alarm? Let's go, that's pretty quick. 3, 2, 1, stop. Right, a burglary alarm doesn't depend on fire or smoke. Oh yeah, people just like to press random things, I think. All right, so what we're going to do, all right, are there any questions about those things? You sort of know we now know what we were doing at the end of last time is. All right. So at the end of what's going to do today is we're going to talk a little bit more about what conditional independencies arise in a belief network, and then we're going to talk about how to actually go about computing posterior distributions of variables given some evidence, how to do computation on these. So what we're going to do is we're going to look at this silly belief network. And hang on, let's get this over here. And I'm going to draw it like this. Where am I? Here it is. Oh, let's all right, so here's this network. And as far as so this is a network I have. So here's an alarm that depends just on the heat of the fire. It doesn't depend on the smoke directly. But whether the alarm goes off also depends on whether someone's been tampering with it. Okay. Whether the story goes that the people leave because of the alarm, they don't directly leave because of the fire or the smoke or the tampering. They just leave because of the alarm. And then that someone you have a noisy report of someone, you have a noisy observation about someone tells you people are leaving. So you have basically a noisy observation of leaving, which is what report is. So it lets you have sort of essentially built modeling noisy sensors in here. Okay. And what we have to do is, as part of this network, we have to specify conditional probability tables. So in here we have, actually I'll do it this other way. I'll do it this way. Whoops, why isn't that working? Is we're going to specify the probability of tampering as true and false. For every variable without any parents, we're just going to put a distribution, the probability that's true and the probability that's false. So in this variable of each variable, we're going to just each one of these just going to say the probability that it's true. For something like smoke with a single parent, we're going to say how the probability of smoke depends on fire. So here we have this, if fire is true, the probability of smoke is 0.9, and if fire is false, the probability of smoke is 0.01. There's a 1% chance of smoke if there's fire, and there's a 90% chance, there's a 1% chance of smoke if there's not fire, and there's a 90% chance of smoke if there is fire. Okay, so we're going to, for each variable that has one parent, we're going to say how it depends on it. And for each variable with multiple parents, for each combination of those parents, we're going to specify how it depends on it. So if there's both tampering and fire, there's a 50% chance of an alarm. If there's, all the way down to the bottom, if there's no tampering and no fire, then there's, according to this model, there's no chance of an alarm. Okay, does that make sense? So we're having a conditional probability of each variable given its parents in here. And similarly for fire, we have there's a 1% chance of fire. And for leaving only depends on alarm. And here, if the alarm is true, then there's an 88% chance that everyone is leaving, but otherwise leaving en masse. Oh, that's a weird number, isn't it? All right, let's change that. Let's fix it 3. Oh. There. Okay, and there's and if everyone's leaving, there's only a 75% chance that someone will tell us that everyone's leaving. And if people aren't leaving, there's only a 1% chance that someone's telling us a practical joke that's telling us that everyone's leaving the building. Oh, everyone's leaving the building even if they're not. So there's a chance of that as well. Okay, so each variable, we're going to have this conditional probability of how it works, of how it does it. And what we can do is we can actually work out, given that model, we can work out the probability distribution of tampering and fire and alarm and leaving and report and smoke. Later on we'll tell you out how these work, but given that model, right, there's only a 2.7% chance of alarm is true. There's a 5% chance that people are leaving, and there's a less than 5% chance that someone tells us they're leaving, according to this model. Okay, so we can actually compute posterior probabilities given these things. And now if we make an observation, the sort of reasoning we might do is we might observe, make an observation, we might observe smoke, and if we observe smoke is true, then we're going to find out that the probability of fire goes up, alarm goes up, leaving goes up, and report goes up. The probability of tampering doesn't change. Right? If we observe that there's no report, make observation of no report is false, then the probability of fire went down. It's less likely there's a fire, and the probability of tampering. Did that change? I think it changed a little bit. Right? If we observe that there's no smoke, right, it's very unlikely there's fire. There's no observation and no smoke. It's very unlikely there's fire. But if all of a sudden we knew there was no smoke, and then we report fire is true, then we can, the probability of tampering goes way up, and observing this also means that fire goes up even though there's no smoke. Right, so we can start, this does sort of inference backwards. So we're going to make observations, and then we're going to get posterior probabilities of things, of variables later on. Okay, that's the sort of game we're trying to play. Okay, are there any questions about that? What we're trying to do, we're going to make observations, because what we're trying to do is how we're reasoning about how observations about the world affect our beliefs. Any questions about that? Yeah.
Can belief networks be bidirectional?
No, they're all single directional. So because the way we constructed it is we totally ordered the variables, then we had used the chain rule and did this. So if you have, there are no loops in them. But we'll talk about later on if you have some time going on, then you can pass them through time so we can have feedback loops. But okay, let's make this none. All right. All right, and this is the. So in summary, what we have is a belief network consists of a directed acyclic graph with nodes labeled with random variables. There's a range for each random variable. Each random variable, we specify what values it can have, and then there's a conditional set of conditional probabilities for each variable given its parents. So we're going, including these prior probabilities for those with no parents. So that's what all we have in the belief network is the graph, the range, and the set of conditional probability tables. And I'll give you the example we'll do. And so when we had, I had a figure of it. Hang on. When we had our familiar wait a minute, I'll find it here. I've deleted it. Oh, let's find it. We had our familiar, no we didn't. Sorry, I deleted my file. Yeah. In this familiar diagram we did before, what we're going to do is we're going to have statements such as L1 is lit, depends on whether the status of, whether it's going, the status of the L1 is lit, and whether there's power in W0. W0 depends on the position of switch 2, whether switch 2 is working or not, whether there's power in W1 and whether there's power in W2. Right? Whether there's power in W2 depends on the position of switch 1, whether switch 1's working okay, and whether there's power in W3. Right? And whether W3 is working depends on whether there's the circuit breaker is working and whether there's outside power. Right? So before we wrote these just logic rules, but now we're going to have probabilities between these about how each variable depends on its parents in here. And given a belief network like this, we might have to specify the range of the variables. We might have these, whether the wires are true, might have values live and dead, about whether there's power coming into them. They were live, remember, otherwise they were dead. The positions of switches might have range values up and down. And the status of a switch might have all sorts of different things that might go wrong. It might be working okay, it might be installed upside down, it might be shorted, it might be just intermittent, or it might be broken. So we have all these hypotheses about what's going on in these. Okay, so we have to specify that. And we're also going to specify the conditional probabilities. The conditional probabilities, for example, the probability that the wire 1 is live, conditioned on the position, the switch is up, the switch is okay, and W3 is live, right? Because they were the parents. So we're going to have all these conditional probabilities. Okay, any questions about that? So they're the three components. There's graph, the range of all the variables, what values they can take, as well as these conditional probability tables. Right. So now let's go back to here. So now we're going to play. So now the question is whether tampering and fire are dependent or independent of each other. And so we'll just play for a while. So we can play in here, we can make an observation on fire. And if I observe that fire is true, the question is, does tampering change? What are you going to predict? No, right? So it shouldn't change. Tampering shouldn't change if I observe fire is true. Okay? So if I observe that tampering, alarm, everything changed except for tampering. If I make it so that it's, whoops, oh, I didn't do anything. I'll make it so that it's true. And if you look at all these variables, then they're all going to change, except tampering didn't. It's still 0.02. So in fact, now we know that tampering and fire are independent of each other, given no other observations. Okay? Does that make sense? They're just independent of each other. Observing one doesn't change the value of the other. Make it none. Now, the next question we're going to do is, if we're given an alarm, we can observe the alarm is true. It changed both tampering and fire. Now, the question is, if I change fire, is tampering going to change? Because if they're independent of each other, tampering won't change. Right? So what do you expect to happen is if you... So we remember before we observed anything, they were independent of each other. So now what happens if I observe fire is true? If I observe fire is true? Right, he says, who thinks it will change? Who thinks it won't change? Who doesn't think? Well, let's try it. So we're going to do here, so we can observe that it's true, and it was 0.634, and all of a sudden it's very unlikely that tampering was true. Right? So they are dependent given alarm. Right? So tampering and fire are dependent given the alarm is true. So although they're independent before we've observed alarm, once we observed alarm, they became independent. So in some sense, so what we often say here is that tampering can explain away fire. When we observed alarm, there were sort of two hypotheses as to why the alarm went off. So we were sure that it was either fire or tampering maybe was the reason for it went off. Once we observed fire, then there's no reason to assume tampering was the cause, was the reason the alarm went off. Okay, does that make sense? And this general structure holds throughout a belief network. So if you have two variables like that with a common child, they're independent of each other, but they're dependent when you observed some child. All right, any questions about that? All right, so let's look at this next one. Let's make it none. So now we're going to look at this just fire, alarm, and smoke, the three on the top right. The question is, if I observe smoke, will my probability in alarm change? So what do you think is going to happen? Yes. All right, so the prediction is if I observe smoke, that the probability of alarm will change. Right, did it change? Yes. Right. Change observation to be none. And if I observe alarm is true, is the probability of smoke going to change? Yes, right. And it did change. So when I observed alarm, the probability of fire went up, and then the probability of smoke also went up. So in particular, alarm and smoke are dependent on each other. Right? So when you have this sort of structure, alarm and smoke are dependent on each other. Okay, let's change this. Now the next question is, are alarm and smoke dependent or independent given fire is true? So I'm going to observe fire. Let's observe fire. Now let's suppose that I observe alarm is false. Will the probability of smoke change? No. Okay? So if I observe, so that smoke was 0.9. If I observed alarm was false, must have changed it a lot, the probability of smoke doesn't change. Okay, everything else changed, but the probability of smoke didn't change. And so in particular, we have alarm and smoke are independent given fire. We have this other structure like this. They're independent given we've observed this. We've observed these other variables. Okay, does that make sense? So intuitively, fire can explain alarm and smoke. So observing alarm changes our probability of fire, which then changes our probability of smoke. But learning, right, so fire changes by probability of smoke, but that's the only way they affect each other. The only way that alarm affects smoke is by affecting fire. If I observe fire, then it's not going to change. All right, any questions about that? And so all the network is all built up of things like this. The whole network is built up of, a whole graph is just built up with essentially 3 components of multiple parents, multiple children, and parents and children. So now I want to know, so I have alarm and report here, and I want to know whether they're dependent or independent. So if I change one of them, so I change report, will alarm change? Will my probability of alarm change? So what are you going to predict? So I'm going to, so what I'd like to do is I'd like to change this to be true. Who thinks alarm will change? Who thinks alarm won't change? Who doesn't think? Who's asleep and doesn't want to be woken? A few of you, okay. So most people think it does change. It's now 0.027. If I observe it to be true, it's going to change. They're dependent. Right, so these alarm and report are dependent on each other. If I observe one, the other one changes. Okay, so they're dependent on each other. Now, and it happens the same way. If I may change the alarm to be true, then that's going to affect leaving, which is also going to affect report. Now, next question is, if we're given leaving, are alarm and report dependent or independent? So I'm going to observe whether leaving is true or false. Let's observe that it's true. If I observe report is false, is it going to change the probability of alarm? No. Okay, does anyone think it might? Who thinks it won't? Good. All right, let's play with it. We're going to observe, make observation. We're going to observe this to be false, for example. Now look at alarm, whether it's going to change, and it didn't change. Okay? Does that make sense? So we have these 3 structures here. And now we know these cover essentially all, so these are now independent given leaving. So essentially the only way that alarm can affect report or report affects alarm is by affecting leaving. And it turns out that all Bayesian networks, if you understand these independence things, these three cases about deference and these three cases, you can understand how all the independence assumptions are imposed by a belief network. All right. Any questions about that? Good. All right. Okay, we've got that. So belief networks are directed acyclic graph where the nodes are random variables. The parents of those node variables on which it directly depends. So it directly depends on its parents and is independent of all of its other predecessors given it. It's automatically acyclic by the way we constructed it. Right? Remember, we totally ordered the variables. And if you give a different variable ordering, you're going to change how this network works. It's a graphical representation of dependence and independence, and a variable is independent of its non-descendants of anything that's not a child of it given its parents. It's because you can always reorder the variable so that the non-descendants, all the non-descendants are before, and it's got this independence assumption. Okay, so that's another way of stating what we're doing in here. So now what we're going to do is when we want to think about how to construct a belief network, we're going to ask what are the relevant variables. So in our case here, we asked what are the, so in our electrical system, we had to ask what are all of the relevant variables, and that answers three questions. What will you observe? What would you like to find out? So we will put status of switches in there. We put whether lights are working or not. Variables that we're going to observe or would like to find out whether switches are broken. We'd like to observe whether things are up or down. We also have this idea about what other features make this model simpler, and a model that allows for wires is much simpler than a wire that doesn't. Okay, the reason you are going to invent other variables is to make models simpler. The reasons why people invented electrons is because it makes models simpler. You can explain the world much better in terms of electrons. The reason people invent diseases is because it explains the world much better than not inventing diseases. So that's why people invent hypotheses. They invent new terminology because it makes the model simpler. So we want to ask what we observe, what we find out, and are there other ways of describing the world to make this model simpler? And we'll talk about this. Then we're going to take what values should these variables take? So now we've got variables and their ranges. Now we want to ask what's their dependence, what's their representation between them. So we want to ask how each variable is generated from its predecessors. And then how does each variable depend on its parents? Then there's the terms of conditional probabilities. You want the second to last point is you want the graph. And the last one is you actually want these conditional probabilities. And this is what we're going to think about when we start building more belief networks. We're going to start building belief networks. Later on, we're going to explain how spelling correction works and how it predicts what things are going to work, how help systems work, how Google cars work, are all from essentially understanding how belief networks work. All right. So now what we're going to do is for the next class, the end of today and the next class, we're going to talk about how to do inference. So really four main ways of doing it, one of which is the first one we're going to do, the one we're going to look at in this class is called variable elimination. We're going to, what's called variable elimination, we're going to eliminate variables one at a time. There are ways of searching, just like we studied searching before. There are ways of searching through belief networks. We're going to enumerate some. We're going to estimate posterior probabilities from other worlds. So people who do diagnosis often use this. We can do what's called stochastic simulation, as random cases are generated according to probability distributions. And there are other methods called variational methods, as to find the closest tractable distribution to the posterior distribution. And it's interesting to know the very first computer was built to do stochastic simulation. So the very first application, the very first computer was built was the ENIAC that was built by the scientists who were trying to do stochastic simulation of how an atomic bomb worked. So the very first application of computers was actually probabilistic inference of trying to work out what might happen when we explode these bombs. So that's part of stochastic simulation. You actually do that in 422. We'll look at that. All right. So now what we're going to do is any questions about that? All right. So now what we're going to do is we're going to sort of abstract things a little bit, and it should become pretty obvious what was going to happen in a minute. So a factor is a representation of a function from a tuple of random variables into a number. That's going to mean by a factor. I'm going to write a factor on random variables just as f of x1 to x. A random variable is x1 to xj. A factor on f, we're just going to write f of x1 to xj. And then we're going to be able to assign some of the values in a factor. We're going to assign, for example, we can assign x1 to be v1, right? So if you look at this, f of all of this, we can assign one value to a variable, and that's a factor on the remaining variables. If we assign all the variables, we just get a number. And we're sometimes going to write this as with this as a subscript. I'm seeing why. Okay. So here's what we're going to. So here's a factor. R is a factor that depends on x, y, and z, and we're going to assign x as the value t. And now that is a factor just on y and z. And we're going to get 0.1 up there because x is true, y is true, and z is true, has value 0.1. Okay, so what's the next value down? What's this value here? What's the value that's going to be here? When x is true, y is true, and z is false, what do we get? So we're selecting x is true, y is true, and z is true. I can't read it. What does it say? What is it? So what we're doing is we have a new table on x, y, and z. We're just selecting those values. If anyone's done databases, this is called a selection in databases. We're just selecting the tuples where x is true. And so what's the value of this factor for x is true, y is true, and z is false? 0.9, right? So this is the factor there. So what's the next one down? Come on. 0.2, thank you. What's the next one? 0.8, thank you. Okay, does that make sense? We're just selecting those tuples where x is true. And now we're going to have a factor. We're going to assign x is true and z is false. It's a factor on what variables? What does it depend on? No. It just depends on y. Right? So once I've assigned x and z, it only depends on y. It's just a factor on y. It only has two values. What's the first value? Hmm? 0.9. What's the second one? Okay, 0.8. Okay. So now we're going to assign x is true, y is false, and z is false. It's a factor on what? What is it? It doesn't depend on anything. It's just a number. Okay? Does that make sense about what this assignment is doing? Just assigning a value to a variable. Once you've assigned a value to a variable, it only depends on the other variables. And we keep doing that. Okay, are there any questions about that? Good. And we're going. Oh, got a lot of time. So the product of two factors is we're actually going to multiply them pointwise. So a factor on two variables. So I put overlines here because these are sort of tuples of variables. So there's a tuple of, so F1 depends on a tuple of variables x and y, and F2 depends on the y and z, and y's are just the variables in common. And what we're going to do is we're going to mean the factors that depend on all three of them, and we're just going to multiply them. So the product of all of those two things. Okay, so let's go through an example of that. How am I going? I've got 2 minutes, all right. So if I have F1 and F2, and F1 is a factor of A and B F1 is a factor on variables A and B, and F2 is a factor on variables B and C. Then F1 times F2 is a factor on both variables A, B, and C. And for this one here, the 0.3 is because when it's F1 of true, true, which is 0.1, times F2 of true, true, which is 0.3, so together they multiply to 0.03. Right? So what's the second one here? If A and B are true and B is true and C is false, what's the product? 0.07, right? So it's multiplying the true, true times the true, false. What's the next one? 0.54. All right, all right, 0.54. Okay, what's the next one? All right, 0.36. Oh, I don't know. There. Okay, that makes sense what we're doing? Yes, it's as though you just did it. We actually have assignment. Do you have assignment? We have assignment.